In the last two parts, we have not only seen Chris use made-up citations that he clearly didn't check that agree with our maths more than they agree with his maths, but we have also seen that the maths makes perfect sense on the globe model and we see precisely what we are supposed to see. Not only has he not addressed any of that, it gets even worse in this part 3, where we talk about telescopes, his misunderstanding thereof, and our conclusion. So hello everyone and welcome to part 3 of my video series on Kryptonite Physics, and today we will be talking about his videos, I believe it is 6 and 7, so telescopes and the conclusion. So first of all, we quickly go through the basics of telescopes. Telescopes are there to collect light. In principle, telescopes are anything that has 2 or more lenses with the primary objective to enlarge something or to make something more visible that is at a certain great distance. Not to be confused with microscopes, although I think the immediate connection there is clear. The simplest telescope imaginable consists of 2 lenses that focus the beam of light on the eye. You can also, of course, do this with mirrors. Both of these telescopes exist. I have both of these at home, nothing fancy, just something to play around with. And you might have seen numbers on telescopes. If I remember, I will put some from my telescopes, maybe both, maybe just one, on the screen right now. I hope I did remember. And they have some typical numbers. For example, the focus length or the focus distance, I think it's called sometimes, and the diameter. So my small telescope has a focus length of 700 millimeters and a diameter of 70 millimeters. So this is a very, very small, cheap telescope. So I got it on a website for used stuff for, I think it was 25 euros. For that, it was a steal, though. Keep an eye out for that if you want to get in astronomy, by the way. So in principle, the larger the focus is, the more magnification you have, and the larger the diameter is, the more light you can collect. That makes sense. The light that comes in here is focused from the first lens onto the second, or however many lenses you have. And of course, the bigger the first lens here is, the more light you can collect. And modern telescopes all have an eyepiece. It has its own focus. It usually ranges from 35 millimeters to 4 millimeters. I think my smallest one is 4 millimeters, and my largest one is 25 millimeters, if I recall correctly, although they are now available in all various sizes. The magnification that you reach on a telescope is the focus length of the telescope divided by the focus length of the eyepiece. So for my telescope, with one of the typical eyepieces that I use, I reach about 35 times magnification. That's a rough ballpark number there. So what about Chris's claims, which is what we really hear? If you recall from his videos, he claims that, and this is the basic premise here, that telescopes magnify more than they collect light, so that the light density, if you will, the flux density of light decreases on average. When you look at a planet, for example, the planet is more dim than what it would be if you looked at it with just your eyes. So for close planets, with the example of my shoddy telescope, this is true. It collects about 100 times more light than the human eye, but it magnifies by about 1,200 times the area. Mind you, it only 35 times the magnification, but the light is spread out over about 1,225 times the area, right? So we have 100 times more light and 1,200 roughly times the area over which the light is spread. So clearly it's less bright by about a factor 10. So this is true. Over-magnification is a thing. It is possible. Chris gives a telescope homepage. They give there the equal brightness eyepiece that you have to use for something to have the equal brightness. So over-magnification is possible, although I would like to add here, when you are at about 150 times magnification, typically you only zoom in on the atmosphere, and you don't zoom in on the thing anymore that you're looking at, but you just zoom in on the turbulence, which gets annoying quickly. Depends a little from telescope to telescopes and on your specific seeing conditions, but that's definitely a thing. So over-magnification is possible. He's completely right there when he says that. And there are a couple of possible solutions here. Well, first of all, don't over-magnify if you can. That's a easy solution right there. If you have the eyepiece, depending on what you're looking at, if you have the fancy telescopes, just don't over magnify if you have to, if you can afford it. The second point really is increased exposure time, and this is a pivotal point in modern astronomy, both amateur and professional. The exposure time essentially is everything. That's because, well, for the eye sees in 1/24 seconds. So every 24th of a second can be reasonably seen by the human eye in terms of frame rate. You know that movies are at 25 frames per second typically, or 24. This is the cinematic look. Anything shorter than that will kind of just look like an in-between of the two, and will be a smooth motion, right? So what about exposure time? Well, beginning with photographic plates in the 1840s, you can do minutes to hours of exposure. Why would you do that? Well, let's say you just do 1 second of exposure. That's already 24 times the amount of light that you have. With our example from top here, let's say that you have 100 times more light over 24 times the time, which would give us 2 times more light than we would get with just the eye. So exposure time obviously solves all of these problems. You can do minutes even, or hours or days if you depending on what exactly you're doing, and if you have a really, really good telescope setup, you can do days of exposure over various nights when you get amazing images even from amateur equipment, right? So what you're essentially doing is you're summing up all of the light. Okay, so you get very bright things. This is what you do if you want to take quality observations of planets, of dim things in the sky. You would do exposure time. For stars, however, the claim is a little different. Chris claims here that because we can see the stars with a telescope, clearly we don't have a problem with them in the first place because they're too dim, but because they're too small to see, even though this is not how that works at all. I will cover that in a bit. But for stars, what really happens is stars can't be resolved. We see them as points. You can't magnify a point. A point has an area of 0. It's only dependent by your eye, by the optical instrument, in this case the telescope, and by the medium the light travels through, so by the atmosphere. So magnification with a point source doesn't apply. They're still points even if you magnify them by 1,000 times. So 35 times magnification doesn't make the star bigger, so the light isn't spread out over any more area. The area is the same. It only depends on the seeing conditions of the atmosphere, which is a more specific thing. But apart from that, you only get more light and you see way more stars. And this is the crucial point here. They are still points. When Chris says here that they would magnify them by some number, you would, if you could actually see them, if they had an area in the first place. They are too small to resolve, regardless of how far you magnify them with amateur equipment. So you only get more light. Of course, the atmosphere plays a role, and up to about 100 times magnification, this is roughly true. And now a quick note on too small to see. Please, flat earthers, please remember that things that can't be resolved don't disappear. It doesn't mean that we can't see them. They appear as what's called an airy disk. They have a certain resolution. The resolution can be even calculated. You bring this up, flat earthers frequently bring this up. This is this angular size of the airy disk in radians, depending on what you see and at which wavelength you observe it, right? So if it's bright enough, we see it. No matter its angular size. We see it if it's bright enough. The photons are still there. Chris, imagine. You have a source that it would be bright enough to see, and you make it as small as possible, even so small that it would fit inside one atom, right? You'd still see it. The photons would still reach your eye. Why should you not see it? You can still see it. It will not look as small as it actually is. It'll look as big as it should, depending on all of the things I mentioned earlier. You know, the medium, the optical instrument, your eye, which I guess is also an optical instrument, the detector, and all things like that. Okay, so from that, we have covered that, and now I would like to go into the errors of Chris's logic, right? So, first of all, Chris, in his video, asserts we shouldn't see stars if we can't resolve them. This is not how vision works. You can see point sources if they are bright enough. The only determining factor if you can see something is if it's bright enough for you to see it, and of course, if it's not obstructed, well, duh. That's the only thing. If you can resolve it or not is an entirely different question, but this is not important. If you can see it because it's bright enough, it's regardless of how big it is. So there's already, it's wrong here already. Second step is we can look through telescopes and see more stars. This is correct. But, he then asserts that, well, thus they must be closer and smaller. Well, but you'd still make them dimmer, right? You're contradicting yourself here. On the one hand, you're saying, well, now we can resolve them because we have magnified into them. And on the other hand, you say, well, they will get dimmer. If we didn't see them in the first place, and they are now even dimmer, why would we see them now? That doesn't make any sense. And we see more because point sources don't magnify. I made this point earlier. Point sources don't magnify unless, and this is what this little star here means, the little asterisk, unless they are, you zoom in far enough on the atmosphere such that you can see the airy disk of the atmosphere, which is very unlikely with typical equipment and with reasonable settings. He then gives 6 points at the end of his video that I would like to specifically address. The first point. Our eyes need 0.01 lux of light to see the faintest hint of color. Citation needed, Chris. Chris, listen carefully. Your sources 1 to 13 don't exist. They say nothing about lux. 2 of these documents actually do exist. They mention nothing about lux and are in this context completely made up. I asked you multiple times to go find them and make me look stupid. You have not done so and you just ran away. This is embarrassing for you, Chris. This is really, really embarrassing. Second point. They need 0.0001 lux to directly see a light or object. More like what we have calculated previously. If I recall, it's 10 to the negative 9 lux. We see the sources that I provided under part 1. Chris agreed with my math in the comment section. I've also shown a few snippets from the last one, but I really want to make his own separate video about it. But he agreed with my math, He agreed with my maths, but he disagreed with my conclusion, which is not how that works. So first 2 points already wrong. The third point, the planets at the distance mainstream science states do not send our eyes anywhere near the light levels needed. We disproved this statement in the last part 2. Go and have a look if you haven't already. Claim 4. Telescopes don't increase the lux level to the rods and cones of our eyes. They reduce the level, a greater reduction of light with greater magnification. First of all, it's a really, really, really weird sentence, the way that you phrase it, but okay. This depends. They do actually increase the light level for stars, because points can't be magnified like that. But for planets, this statement in general is correct. Lucky for us that plenty of light reaches us from for example, Mars, from the closer-ish planets. So this is the only statement that I can give a passing grade here. 5. If telescopes don't increase the level of light to the rods and cones, stars cannot bet too dim to see. It should be a B here. They must be too small to see. So many spelling things. Too small to see is the thing. I explained this just earlier. Photons would still be there. They would just be unresolved. The source would be unresolved, and it would be an airy disk at the smallest. The 6th statement. Telescope's magnification alone makes more planets and stars visible. Thus they must be closer and smaller. Did you try that? You know that you could build or commission a telescope that just magnifies and doesn't collect more light than you do. You could absolutely test for that. Please, I encourage you to do that and see that you're wrong. This is an extremely good test of your own hypothesis there. Other than that, we talked about that this is not the case. Telescopes magnify. They really can't magnify point sources, so they only collect more light, and this is why we can see more of them. Chris, I'm highly looking forward to your responses in the comment section. And with that, this is part 3. I think I will do a part 4 where I just talk about Chris's funny replies and our conversation in the comment section. So yeah, I hope you will tune in for that, and other than that, I hope you enjoyed watching. If you Not so quickly there, past Olaf. I have, of course, done Chris's experiment that he has been touting in the comments of a couple of his videos about the telescope, and you put the candle or put a small light this and that far away, and of course I did all of that. You can see, I hope I can flash in the pictures here. You can see that I put up my telescopes, and I put a candle at about 15 meters away. And from that, I observed the candle with two of the eyepieces, one 12mm and one 20mm eyepiece. I will flash the pictures here. This is the 20mm picture, and this is the 12mm picture. And from that, you can, I don't think, I honestly can't say that I see much of a difference between those two pictures. They seem like one of them is just zoomed in. But either way, it is certainly more dim than when you look at the candle as such directly. Well, somewhat unsurprisingly. But this is perfectly well what we should expect. And if you would have wanted the candle to be more bright, I would have just increased the exposure time. Of course, I should mention that between these two pictures, I let the settings of my camera I didn't let it vary. It was precisely the same settings for both of these images. Yeah, and so which is Chris's experiment complete, and I agree with his with his basic conclusion that yes, telescopes can make something more dim than they originally were, seeming to the human eye, which is in terms of flux per area, which really isn't a surprise, is it? If you enjoyed it a lot, maybe consider subscribing, and if you enjoyed it, maybe consider leaving a like, and I will see you in the next video. Until then, goodbye.